Good night, everybody, and thanks for joining us tonight. The general topic would be trying to use machine learning for the non-proliferation of nuclear weapons. But the focus on this would be on the explosion monitoring for low-yield nuclear weapons. So just a bit of background. What we're trying to do is that you're looking at a few different fields that are generally linked together by, like, picture an umbrella, and then we have these different fields, and we're integrating machine learning into this umbrella. So we have the intelligence domain, and there are many different definitions for it, but the main one one of the general ones I like is the intelligence is secret. It's a state activity to understand and influence foreign entities. So basically, if you or your country wants to work on something, you don't want anybody else to find out, but you're even more interested in finding out what secrets that they have. And then this always goes hand in hand with war and warfare. We use them interchangeably, but usually warfare is the actual fighting bits. But with intelligence, you want to focus in on a lot with the strategy. And the strategy, you want to always have it behind your mind, the capability and the intentions of your enemy. But the thing is that it's more difficult to use intelligence to figure out the intentions because, what is someone thinking? But you want to know the capability. And that brings us to weapons of mass destruction. And when you think about weapons of mass destruction, there are different branches. You don't only have nuclear weapons, there's chemical and biological as well. But for our sake for today, we'll be looking at the nuclear weapons part. And when it comes to knowing the capability, the reason I started off here with the non-proliferation of weapons being the focus is that there's a part of the strategy for war and warfare that's not just all fighting. A big part of it is deterrence. And you want to avoid fighting because you must also know your own capabilities. So if your country doesn't have the capability, for instance, like the UK, it's very vulnerable to a nuclear weapons attack. The way it's designed, its position, and then the way how London is very exposed with the Thames going straight through, you can have a nuclear warhead going through straight in the middle of London, and it's very vulnerable. And because of your own disability, you have to weigh out what's best. So the non-proliferation acts, all these treaties and diplomacy and allies with NATO, it comes in very handy when you know, okay, let's not go into a whole who has the bigger guns battle. Let's try to use a method of deterrence. So I went on a bit about deterrence for a reason, and that's because right now you don't hear about nuclear explosions as much. So you may wonder, why do we even need to look at this? So let's first look at nuclear explosions in the past. When we think about this, we think about an obvious mushroom cloud, some gigantic explosion. Let's just look. I like to look at this video. You don't need to hear it. It's just a clip of the, this was the 1958 explosion in the Marshall Islands, just to give an idea of what
came up through the water. They could tell how long it was for the shock wave to hit a certain rocket trail, which gave them the propagation rate of the shock wave. It was about 2.5 miles from them.
Test.
The
So
rockets
see how
went
massive
off,
this
and then
was.
suddenly this gigantic column of
You're
water
thinking,
shot
if
straight up into the air.
Weapons cause such a huge impact, why do we need to go through all these methods of detection? So it's not like a Godzilla movie, because actually a lot of them occur underground. Up until 1957, yeah, a lot of them were above surface, but then in the 60s, there was another law that was passed, so they didn't have as much above ground, it was mostly underground. And during the Cold War, 75% were actually done really deep. And the deeper you go, you can actually have explosions that are very difficult to detect and almost undetectable depending on where you are on the globe. So there was this treaty the Comprehensive Nuclear Test Ban Treaty in 1996. So generally before that, we had a lot of testing going on. On record, it could have been more that we didn't detect. There was 2,000 tests that we know of worldwide. That was between 1945 to 1996. And then the post-treaty time, there was only 10. 2 in India, 2 in Pakistan, and 5 in North Korea that we know of up until 2017. Now, you would think, okay, it's only 10 compared to 2,000 nuclear tests. So maybe this is not really something we need to focus all our energy on. Maybe we should look at biological warfare. But there's a reason we still need to figure out if there are things that's going on that we're not detecting. There are low yield types of nuclear explosions. So nuclear explosions, they get a bit tricky to detect when there's small yields. And worse yet, these small magnitude events get even more lost with other small magnitude, for instance, seismic activity or just overall noise. So there's the International Monitoring Group. That's one of the main centers that you can try to get data on for this sort of thing. And they keep a really good watch on the underground nuclear testing. And the thing is that they have so much stations to monitor these, and yet it's still, to be able to find a nuclear explosion, it can be hidden so well that it's still looking for a needle in a haystack, because you can have some really covert explosions that are really far deep in tunnels, deep underground, and low impact explosions, not the type that would cave in an entire mountain like what happened in North Korea. So what we want to do is that the aim is that you want to shrink the haystack. So it's not like the best case scenario, but when you're handed a scenario that is really difficult, you want to shrink that haystack. So the IMS, and that's where the paper that I'm discussing tonight, that's where they got their data from. That's the International Monitoring System. So they have 4 detection methods. There's the hydroacoustic. So the hydroacoustic is the technology that is used to measure in the water pressure caused by sound waves. And then the infrasound, which is what we spend most of the time today in the presentation on, not because it's the best method or anything, that's just what I'm focusing on temporarily on my research right now. So you monitor the, it's mainly like, it's mainly the atmospheric nuclear explosions, but I'll explain this a bit more just now. And then there's the radionuclide. So it's to try to get the noble gases like xenon in the atmosphere, but it's not just for explosions. This is used for, there's actually a really, really nice study that was done only 2 years ago on detecting these sort of noble gases on the actual material of it could be any sort of thing that's trying to cross a border of a country. So they try to use the radioisotopes, but that's a whole other thing as well too. But it's very fascinating. That's why I went off topic there on it. And then there's a seismic, which is actually one of the the cool parts of the detection methods, because it is to detect underground nuclear explosions. But as you can imagine, the amount of seismic data that floods these sensors constantly. So yes, they have some really good stations out there. And what they do is that they consolidate the data and then they send it to the IDC, the International Data Center in Vienna. So there have been quite a few studies where they were openly able to share their data with the researchers, which is really good. However, because this is a part of intelligence and security, not all the latest methods or data are released. So that's one of the setbacks when you're trying to come up with a thesis or literature review. You have to sometimes you see, the thing is, when they declassify things, is really old, and the military holds really dear to a lot of these publications. But there are some that are published, and we're very grateful, and also grateful for their data that whenever they do choose to share it with researchers. Now, what we're doing here is nothing new. And so, okay, you may think I mentioned the treaty. Since 1996, there have only been 10. Nobody really seems to be doing nuclear explosions anymore. It seems as if, okay, yeah, there's a lot of things out there to try to detect it, and nothing's coming up. So maybe most people are adhering to the global treaty. So why do we need to try to find ways to think, okay, maybe there are the low yield explosions, or maybe there's something we're just not hearing? The point is that we are on an eternal quest to find what your enemies are up to. And the reason you need to try to see what's not there is that this is a really funny example to remind you that you need to keep looking for some sort of build up of someone else's army, like a secret buildup of someone else's army. For instance, in 1915, you'll wonder why I have a pigeon here, but there's actually a real CIA declassified paper where they talked about the whole Britain, Germany, espionage, counter-espionage issues. And Britain had this theory that the pigeons were part of the espionage. So the pigeons, because if you have a spy in Britain and you don't have sophisticated technology, how are your people getting communications with their home? So they believed that the homing pigeons were part of it, and they called it night signaling. So, of course, it was a theory at first. But then after some more digging, they realized that it actually was true, and they actually were killing pigeons, like a lot of pigeons, spy pigeons died, and obviously the innocent ones. So that was just one lesson you remember, you keep in mind when you're trying to get intelligence for safety, that the obvious needs to even be dissected and not take things for granted. And then we had times when the entire USSR was just this whole landmass that you couldn't access. You had no satellite images from like 1958. Imagine a world where we don't have satellite images to explore this entire huge mass. We have no idea what they were trying to do all that time during the Cold War and World War II. So then you would try to think now, when we got satellite imagery and you can canvas everything, then, okay, maybe we don't need to look further. What we see is what you get. But no, you do need to look further, because there are a lot of clandestine operations going on. If you know there's a way to look, you'll find a way to hide it. So today, that brings me on the point, everything looks calm when it comes to nuclear weapons. It's peaceful. The water is peaceful. The land, you don't have seismographs blowing up. You don't have these anomalies right now. It seems that the ban is working. But there are regions of interest that we have limited ability to do surveillance on. I didn't want to go off topic anymore. So there's this region in the South Asian Sea called the Spratly Islands that China claims, but it's not really theirs. And they want to restrict people from doing surveillance there. And one of the possible things they can be doing is low intensity nuclear testing. So you want to find a way to be able to do detection from a long distance, because some of the methods for seismic, actually, you can do detection, but the further away you get, it's very difficult to differentiate noise from an explosion or an earthquake. So everything can just sound like noise. So let's go back to the detection. Out of the 4 detection methods, we would look at infrasound. Infrasound is an acoustic wave with low frequencies. And the IMS, the International Monitoring System, they have all these right now. It's about 60 in total. Well, these are planned, but they come to the 60 right now. And it's all over about 35 countries. Notice where we kind of lack monitoring stations, not pointing fingers at China or anybody here. So the stations monitor globally, and the thing is humans can't hear this because it's inaudible to us at that frequency. So this is where all that priceless data is coming in from. The reason infrasound is good to look at when it comes to nuclear weapons detection is that it travels long distances with very little dissipation. This is an IMS station that it measures the micropressure changes in the atmosphere. But again, this is not something new. In 1883, there was infrasound occurrence that was actually volcanic. And when I mean it, when we have very little dissipation, it traveled the globe 7 times and like broke windows that were hundreds of miles away. So infrasound has benefits when it comes to trying to seek out anomalies in possible nuclear weapon explosions. But we have all these other different sources of infrasound, sorry. And the problem is that, yes, we have it from nuclear chemical explosions, volcanoes, you even have from generated from airflow over mountains, satellite space debris, aircrafts, and then a lot of it can just be noise. So how do we even classify all of this? So the main problem that I'm getting to in all of this is that we have classification problems. Is it noise? Is it a volcano? Is it a nuclear explosion? Or is it a mine somewhere? And the thing is that we can be picking up frequencies all now. And because of the very, very high misclassification rate, it can just be recorded as noise. And the thing is that currently we have classification systems that's not just only human, but we have some computational methods, but we also have to heavily rely on human analysts. So that's very slow because expert human analysts is very expensive, and the nature of the type of threat an explosion can be. It may not be a destructive explosion. It can be testing small bits over a long period of time. And if you only realize this long after, that lag is not something you as a safety or war strategist want to be falling behind. Because if you fall behind in your enemy's capability, if you're busy looking somewhere else, you will not be able to catch up. And in history, this was the case in a lot of times, and you learn from history and you want to not repeat these things from happening again. So you want to do it faster, and you want to be able to do it more accurate. So what the ultimate goals here would like to be is that first you want to be able to reduce your reliance on human expert analysts. And this goes back decades and decades ago, where we started off with pigeons, and then complicated communication systems developed because of war. Advanced technologies were pushed in times of when we were challenged as a human race or as a country. And we change our technology drastically when we're threatened to. And there were many cases where we created unimaginable ways to replace humans, and we got it more efficient. So this is just one of the many other ways. So it's to reduce human expert analysts. We're not saying fully automated, but at least try to reduce it. Then false positives in the seismic research domain, they have had actually some pretty good accuracy with some of their modeling, but a lot of the downfalls actually ended up being a lot of false positives. Actually, I know that's seismic. I know we're not dealing with that right now, but generally, that has been a sort of a pattern you're seeing in some of the research papers. And then we want to try to make it faster. So we want to do some real-time classification and try to automate it instead of just having so much data coming in, and it just takes forever to go through that. So there is a paper from the proceedings SPY. It's the Chemical, Biological, Radiological, and Nuclear and Explosives Sensing from 2018. And this was one of the first research papers actually that gave me a good grounding into trying to understand how to approach the threats classification problem. So they did a statistical comparison of the deep learning architectures. It all started off with a basic, with a first, not basic, sorry, artificial neural network. And after working out this, they developed 4 that they tested each one and try to see which would suit the classification problem best. So we're looking at these 2 right now because the self-normalizing one actually performed the best. And so the deep neural network is basically our artificial neural network. We'll all know this, that is just a multiple set of layers. So we have our multiple hidden layers. And the difference is that the self-normalizing one, we have our SELU, ICSLU nodes. So we have our 3 layers here of our nodes. And the difference here is that the activation function, the SELU activation function, and the companion dropout, it basically, it creates a technique that this is the main thing we have to focus on, which is the self-normalizing property. And what it does is that one of the things that I was looking at with the actual theory behind it is that the way it allows you to train without saturation. And there are a few other reasons actually that ended up having this method be better when it comes to regularizing your data. I actually should have shown some of the data, but okay, ignore that, to get a better idea of why we needed to do this, but I'm sorry about that. This is actually the 4 types of events that were used in order to conduct our experiments. Well, their experiments, sorry. So the neural nets that we just mentioned, they were tested on these infrasound signals. And these are 4 natural events. It's the auroral one, because if you remember the diagram, you can get it from the aurora borealis, then from the mountain associated waves, microbarometers, and the volcanic eruption, which is sort of like one of the most obvious ones. But the thing is that visually we can see the differences here. So classifying, if you already have these 4, that's one of the problems with this study, was that they tried to classify 4, but not 4 that was also intertangled with noise. So that's one of the drawbacks for this paper, but obviously it's a stepping stone. So we're looking at these 4 natural events. But just keep in mind that in reality, nobody's going to give you this clean, data with 4 sets. So that's one of the major problems when you realize how accurate it was. So like I mentioned before, the SNNs were significantly more accurate. The LSTMs, even though it's really state of the art when it comes to a lot of other sort of sequential modeling, it fell really, really behind in accuracy in this one. This is not the only study that I've seen where the LSTM performed poorly with these sort of similar sort of explosive metrics, and the DNN and SNNs performed better. So there's a bit of consistency there. So this is just a little more detail on the results. So, oh, I forgot to mention, Lotus, that's the actual data set, that the name of the data set that was used to get the data from the 4 events from the waves. So to get this data, should have put that there, sorry. So basically SNN, it was a superior model, and it was determined by our statistical analysis, and we accustomed using our precision, recall, F1 scores, and all that. And yes, it did perform best in them, but we need to keep reminding ourselves that this was done not against noise. It was just the classification of the 4 events. However, it is used as a stepping stone to sort of show that, okay, we can tell the difference in these events. So then we can go a step further to try to mimic underground mining explosions or deeper explosions, and then try to differentiate between a type of explosion and a type of maybe of volcanic eruption, and then maybe realize, okay, we can tell the difference in this cluster as opposed to noise. You may not be able to tell the difference in a weapon explosion and an earthquake, or sorry, and a volcano eruption, but at least you can know that it was not noise. So then you can further analyze it. So that's what I meant by making the haystack smaller. So you end up with a smaller haystack, but regardless, nevertheless, it's still a haystack. So in the real world, one important thing that we need to realize is that to build on other research that's out there, because this is not something novel at all. It's being tried and tested continuously. And one of the main things is that we can't just say that we're using a data set and plug it into models and use that as a guidance and when it comes to trying to figure out what other people are doing. The reason I'm mentioning that, and I have this here, is that there's this thing called data poisoning. And when it comes to your threats and your security, the data is not always what it seems, which is where the part of questioning the data authenticity comes in, which is a whole other job for analysts. So when a data scientist has to work in a certain domain like this, you have to take extra time, or the analysts have to take extra time before you actually get your hands on data, because you can actually be fed data on purpose that is misleading. That will make it more difficult for you to find that needle in a haystack. There are situations where countries actually try to publish fake maps and pass it off as real satellite images. It's no different when it comes to sensor data that could be throwing you off when it comes to your pattern recognition. So that's one of the big problems when it comes to making classifiers in a sort of weapons of mass destruction domain, because you always have to be aware that someone is trying to coerce you or mislead you with wrong data and wrong patterns. And that's one of the bigger challenges, even more than the efficiency or the accuracy of your modeling techniques. So from this point now, where I need to go, because the whole point of this work is that I'm trying to come up with a thesis, and I have to frame the research proposal, and that would also require looking a little more into the seismic aspect. Then after the seismic aspect, look at the methods and the way they collect data, ensure that I can get my data acquired, and we'll figure that part out, the data acquisition, and I wouldn't be able to work on it alone. I'll actually have to work with a couple other people on the data part of it alone. And then one of the expertise, which was a similar but different research, is looking at the nuclear material detection at border crossings of countries, but that is using the radionuclide. So that may be another part to consider before finalizing and framing a final research proposal. So yeah, so it does require a bit more fine tuning. So that's until December for me. So hopefully I'll have something more framed in a couple of months. These are the two main references that I've used. I've used a few more, but these are just the general ones. This is actually the CIA declassified documents on the pigeon espionage. I know it's really funny, but I thought it was interesting. So I hope you enjoy the project, the presentation so far. Thanks for watching, and if you have any questions, either now or afterwards, you can always email me.
Yeah, thanks, Nidia. Interesting stuff. One question I have is, there's a lot of work in the past on signal processing. So is any filtering or signal processing done before passing it to a neural network, or is it just the raw data goes into the neural network?
Actually, yeah, good question. The SIGINT, the SIGINT, signal intelligence, as you said, is really, really old. It's been done for so long. And in terms of this application, it's not raw. When the analysts do their processing, they do their not first, but quite intensive bits of processing before it gets to like a data analyst person. So we're not dealing with the raw data, because I don't think that's a lot of work. And I don't think, I think they have their own experts to deal with that part, like signal processing, because that's the whole field of study as well too. So yeah, they have to do some more cleaning and stuff before it gets to the analyst.
Okay, okay, yes, so that's interesting. I didn't realize they do it separately. Yeah, no, it's interesting stuff. I mean, I don't know much about this area, but the only thing I know is there was an interesting movie I saw about the Indian, how India became a nuclear power, and how they had to do their testing, etc., to avoid the satellite, the U.S. satellite detection, etc. But yeah, I forget the name of it. Maybe one of you have seen it.
The thing is, I would look and see, because I should watch it. I actually don't know that movie, but they have so much applications for machine learning in the army right now, because you can't have intelligence without it right now. It's like a given, but a lot of their work, it's not published, and a few of the things that are published is like a small, it's the tip of the iceberg of it, but it's enough to sort of get you onto a path that you can come up with an idea to pursue for research. So it's really fascinating, but at the same time, there's a lot you don't know. So you don't know if your research is relevant at the time as well. So that's what you need to spend some time doing before actually finalizing a topic.
Yeah, actually, I did have named the movie Parmanu. Yeah, that was it.
Is it an Indian movie?
Yeah, it's Indian movie.
Okay, I'll take a look.
But thanks, nice presentation. Nothing else from me.
Hi, Nidia. One question. So you had the four basic signals from the like the mountain, and then the earthquakes and so on, right? How does the nuclear signal compare to those? Like, is it pretty similar or sort of distinctive? Because I mean, I get the idea what they're trying to do. They're trying to go deep enough so that it looks like one of these things, right? But like, if like known signals, if you were to compare them, how do they match up? Is it like an exact match, or you could see that it's similar in some by some factors?
Some of the studies, what they do, they have two things they do. They do either the simulated explosions, or when it comes, so for this one, they do simulated explosions or explosions that are like from mining explosions. But the seismic research, they are the ones that they do both simulations, and they actually use artificially induced underground explosions and mining explosions, because there's a large data set, if I can remember the name of it, there's a seismic research paper where they used over 200,000 data points, and I think it was kind of a balanced data set, if I remember correctly. So two of the classifications there, the classes were artificial. One was artificial simulated explosions, and then they also used mining explosions. And the good thing, well, the classifier just was able to get explosions, but obviously you can't differentiate. But it was, so this study, it was actually able to know that something was not noise, but it said all the explosions, regardless of simulated or the real explosions, they said they were all earthquakes. But so there's actually the confusion matrix for it. But the good news at the end of the research paper was that at least it classified all as something, because before that, the accuracy was so bad, everything was being misclassified as noise. So how you try to mimic your explosion or your nuclear just something to detect is either simulation or something similar. So they have the waves, like the waveforms of how one would really look, and then you match that. So it's not bad, actually.
Okay, pretty cool. So like, what? Any idea what they do with the waste from these explosions? Because I mean, it had to go somewhere.
Well, if they're still doing it right now, well,
yeah.
they sometimes they do it so deep that now you're supposed to put it like underwater, and it's supposed to be okay if it's either buried very, very deep in the earth or both very deep in the earth and underwater. That's what they're supposed to do. And let's hope they're not doing anything else, because then you can get contamination. But so far, the methods of burying it like that, either deep in land and underwater, or just very deep in land, it's supposed to be okay.
Yeah, I was just thinking about if you have any other type of data other than these signals that could kind of hint, something suspicious.
Yeah, the thing is like, for instance, like North Korea, to get to their waste, well, North Korea is one, insane place, but then there's the Spratly Islands. Now, if you are hiding nuclear waste, you want to have an area that's totally guarded. Now, Spratly Island is owned by, well, nobody really owns it, but it's like Philippines and not China, but China thinks they owned it. And they went and build up all these artificial islands now. So they're even making more man-made islands, and they're in the middle of nowhere. But if you look at it on Google Earth, you'll realize that they have all these towers, and it's like this whole big area of surveillance. But also, we don't know what they're really testing. So one of the hypotheses is that they are also conducting low frequency types of testing, and they don't want anybody surveying that area. So if they do have waste or something like that, you can't actually go and access it physically as easily. So you want to try to find ways to also detect this from far, because you have pretty good classification of seismic activity. If it's seismic activity or an explosion, it's very good accuracy when it's close. The further you go, it's horrible. The accuracy is really bad, and it can just seem as just noise or is totally undetected.
Oh, interesting stuff.